Ever wondered how fast a chemical reaction takes place? You've noticed that if you put, for example, sodium or potassium on top of water, you could even have an explosion from the hydrogen gas that's given off. But if you put a nail into a beaker of water, you're going to wait a long time for a single bubble. Okay? So things react at different rates. Any of you who've put an effervescent tablet into a glass of water, you will also note an interesting thing happens. The tablet effervesces, and in the beginning you get a high amount of foam, which means that the start of a reaction, it's normally quick. But as the time goes by, the foam stops, but you still see the tablet and it's effervescing less. Okay? So we generally have rates of reaction quick in the beginning and fading out as time goes by. Now, before we get to and start analyzing that, we need to have a look at something and revisit something we've spoken about before, which is the activated complex activation energy, EA, and we need to talk about endo and exothermic. So we're going to revisit that very quickly. Okay? Now, first of all, in any chemical reaction, we have, and this is a very important thing to think of, we start off here because we have reactants, and they go to products. All right? That is critical. We have a reactant side and we have a product side. Now, why, for example, I'm just going to use the classic N2 plus H2 gas going to NH3 gas. I'm going to put a back arrow there. Don't worry about what that's about for the moment. Let's balance it 2 and 3, 1 plus 3 moles. Now I'm going to draw a line down over there and I'm going to say 2 moles and draw a line over there. Now, what we need to understand here is we've got reactant A and B and product could be C and D. There could be 2 products coming out. Or 3. Imagine if we put a carbonate with an acid, okay, we're going to get carbon dioxide, water, and a salt, aren't we? So we can have quite a number of products coming out as we do these reactions. Now, let's stop there and say, okay, let's just ask ourselves something. Why, I know we've done this before, but here we go. There's our hydrogen, and let me get over here. Here's the nitrogen, guys. There it is. Okay. Now remember that N2 and that H2 that are sitting there, these guys here, this is a molecule and a molecule. A molecule of N2 and a molecule of H2. Why on earth would these guys want to split and go bond with something else? The answer is they don't. If I put this into a container, all right, we now have to understand it'll be a closed container. We'll get to that as well. But if it's open, the gases will fly away. So let me say I've got, and this is my pot. Okay, it used to be a magnet, it's now a pot. So I go and I put these guys inside there. They're not going to do anything. Because why should they? They are happily bonded in a very low energy state with each other. The nitrogen has got a triple bond between it. So there's quite a lot of energy involved there. The hydrogen's got a single bond, but even so, it's still quite a bit of energy that's involved. Now, the answer is simple, they don't. We have to take them to another place, all right? So we have to, I'll pick up with those guys again just now. We have to take them to another place, and that place is called the activated complex. Okay, remember that from the previous sort of studies that we did, the previous work. So let's just draw a graph here, all right? And I know we've been through this before, but bear with me. This is over time. Now, this axis is potential energy, right? Potential, and don't matter what it is for the moment, all right? Here's our graph, okay? This is A and B. This here, okay, is my reactant side, and this is my product side. This piece here, I like to tell my students, it's this interim phase here. It's the interim phase there. Between reactant and product, there's another phase that sits there, okay? It's like you've got a piece of meat or vegetables. Before you eat them, you cook them. That's the interim phase, is the cooking phase. That's a new one. This is where we cook them. Or freeze them, okay? But we're going to cook them. Because what did we say? We said, first of all, that this over here was called EA. And we said EA is activation energy. Activation energy. Remember way back, we said that is the energy to break up. The breakup. That's the breaking up side. The other side of this is the making up side. Okay? Because what do we have to do? We have to apply energy to break apart the N triple bond, the hydrogen bond, so that these can all combine and form new products. And we call this interim phase over here where we're cooking them, we call this interim phase here, up at this point, we call it the activated complex. Okay? It's got all of our bits and pieces in, and it is where we are cooking them. Okay? This could be C plus D. Right? The next we said, all right, now this is energy initial. This over here is energy final, isn't it? So what is the change in energy here? For those of you who've done it with me before, it's always E final minus E initial, which in this case, E final is less than E initial. So it must be a negative, and we call it delta H. Okay? In other words, it's the heat energy. Okay? In this case, given off. All right? It's negative. There's less heat in what's left over than there was in the beginning. Right? So heat has been removed. Essentially, it's like freezing ice cream, isn't it? You've got the constituents, you remove heat from it, they freeze. Okay? So there's less heat in the final product. It's lost heat. We actually have to just look at the next section. Just let's look at the other curve while we're here. All right? All right? And the next curve is the endo curve, isn't it? Right? So this is E final. Sorry, my bad. This is E initial. E initial. This is E final. And delta H, we said, is E final minus E initial. And delta H in this case is greater than 0, which means it's endothermic. And remember, an endothermic reaction needs heat. Okay? It asks for heat. It is, in fact, this is, if you like, stored heat in the reaction, isn't it? Same again, we can just put in the other lines. This is EA over here. All right? The activation energy, my bad, is there, isn't it? EA is the activation energy. And the piece on top, okay, I said this was the breakup. This over here on the other side, I can't remember, what did I use? What did I use? I used making up, I put blue, okay, making up, blue, and this is the making up here. Making up the product, and in between the green bit was the activated complex. Okay? It's where we do the cooking, essentially. All right? So that now is an endothermic, and the previous one up above was known as exothermic. All right, and remember we spoke before about it. This is exothermic over here. This is exothermic. Why? Because heat is given off. Exo, to exit is to give out or give off. So that gives off heat. Now, so we've got those two separate curves that we've got. Very important that we know them. Okay, we've got that, all right? So this needs heat to continue, right? The endothermic. Just let's clarify here. Homogeneous reactions. Homogeneous and heterogeneous. Heterogeneous reaction. Okay? Homogeneous reaction, all, okay, reagents in the same phase. In the same phase, i.e. they're all gases, or all liquids, or all solids, okay? Highly unlikely to have all solids, okay? Heterogeneous, okay? They're in different phases, okay? And you have got, you could have different phases. You could have a solid plus a liquid, okay, etc., etc. All right? Now, let's just have a look at the next page of this, all right? Let's have a look at the rate of reaction, the actual rate itself. The rate of a reaction. Firstly, we know, okay, like I've said, calcium carbonate plus an acid, quick fizz, okay? If you put lemon juice on it, you're going to wait a while. It's a weak acid, right? And we've just done organic. It's citric acid, so it's a weak acid, right? Now, what do we do? How do we define or measure this word rate here? How's it done, all right? Well, you'd ask yourself, what are you doing? You're converting something to something. So it's going to be, it's measurable. So we're going to have something like, for example, you could have grams per second, okay? You could have change in concentration per second or per minute. You could have mass of gas per minute, okay? So these are measurable items. So when we're looking at measuring a rate, we're looking at a measurable item, okay? It doesn't help us if we can't measure it, okay? You could, for example, take change of pH per whatever as well. There's a whole load of different measurement items, okay? So we're going to look at, we're going to look at a few, okay? Moles, concentration, or mass. So let's look at a time graph over here. This is time. This over here is going to be moles, or, what is the square brackets? Or mass. That's concentration. Okay? That is concentration, something that we all wish we could take to get us going. Now, let us have a look at a reactant first. This is our reactant. Okay? This is always T equal, at time equals 0. Okay? How much reactant have we got? Let's put it in red. We've got all of it. Okay? The full number of moles or full concentration or mass. And what happens over time? Over time, this starts to drop. Okay? All right? Never mind that little bit there. All right? We'll get to that, what's going to happen further on. But just conceptually, you can see that this is starting off. Now, look, just have a look here. Look here and look over here, for example. Okay? This is the tangent to the slope. So the green is actually the slope of the line. Okay? The slope of the line is, for example, over dt. All right? In other words, rate of change of concentration with time, rate of loss of mass, rate of whatever it is. All right? It's a slope. All we want to go is in the beginning, okay? In beginning, it's high. Okay? After time, it is low. Lower. Okay? Until it gets to a flattening out point, but we'll get to that in a few moments. Now let's have a look. That's the reactant. Okay? Let's look at product. Okay? Take the same graph over the same time, t equals 0. This is going to be equal to moles, concentration, mass, whatever, something we're measuring, okay? How much product? This is product. How much product have we got in the beginning? Okay, let's go to blue. All right? Okay? None. There's no product. Because when it starts, when I drop the tablet in, there's no antacid in the water or nothing. No minerals or any. It's still got to dissolve. But can you see once again, the slope of the line over here is steep. So the slope, okay, which is actually the rate of reaction, okay, it slows down, okay, till we get to a constant rate. All right? So when it gets there, it's a constant rate, okay? Just let's leave it, it's flat actually, okay? But it's not changing anymore, and it doesn't change any further, okay? So what you've got is you've got a reaction where we start off fast, we generate product, and we generate product fast, and we lose reactant fast. Now, all right, let's have a look over here at a few things. The first thing we've got to do, we have to understand what affects the rate of a chemical reaction. What affects the factors? Okay, this is the factors that affect the rate of a chemical reaction. Now, why do we need to know this? Obviously, if this reaction is going to be pretty exothermic and fast, you need to know about it, because you kind of don't want it blowing up all over everybody or everything, right? And you need to be able to have something big enough to collect the gas if that's your job, okay? So it's a very critical part of chemistry. Some reactions are slow that we could leave them for hours, okay? It can take a while for things to happen. So not everything happens fast for a very good reason, okay? And we also need to know this. Why? Because we want to control the reaction, okay? Especially if it's nuclear, we kind of want to control that. So we want to control the reaction, the rate of reaction. You don't want it all to go whoosh, and then it's all happened and it's all over with, okay? Like a firework. No. You want it to go at a slow and steady pace. Why? So that if you're collecting it at a rate that suits you, okay? You don't want to all of a sudden have a huge chamber full of ammonia, okay? You want to create it slowly. All right. Let's have a look at the things that affect a reaction rate. Number one is temperature. Temperature, okay? Normally, for example, if you take sugar or salt, if you put a pile of it in a pot in cold water, you can stir it till the cows come home. It's not all going to dissolve, is it? It's slow. As you heat it up, so your rate of reaction generally increases. Let's think why. Because with heat, what are you doing? You're creating more activated complex. So the temperature creates more in the activated complex, doesn't it? Zone, I'm going to call it. We're going to have a look at that a bit further when we look at Boltzmann's curve, okay, which is generally very often asked, by the way. So temperature, okay, is going to affect the rate of reaction. Number 2, what about the concentration? Okay, the concentration. The more concentrated, the quicker. Why? Because there's more moles of the chemical coming into contact with the other one to allow the reaction to go quicker. If you've got more moles, obviously, you're going to have more effective collisions, aren't you? More collisions between the particles. Because at the end of the day, what are you asking these to do? You're asking this thing and this thing to actually join up, right? Now, let's take our ammonia and our hydrogen. Hydrogen's got 1 electron. Here's my hydrogen. This is ammonia. It's got 3 open electrons, right? I need to have this electron coming at the right angle, okay, and with enough speed to jam this electron in so I can't get out again. I have to do that 3 times to create 1 ammonia molecule. Let's think. 1, 2, 3, NH3. So I've got to bang that in. So I need to have, let's just back step a bit. I need to have a high number of collisions. Okay, number 1, all right. Lots of them, the more product I can make. Number 2, I must have enough energy to collide. Okay, that's B. And number C, they must be correctly oriented. Okay, C. What do I mean by that? Well, I'll explain myself now. Okay, here's my nitrogen. Okay, there is my 3 parking spots. I've always used red. Okay, there they are. Okay, now I need a hydrogen to come along. Okay, there's my H. But now, if it comes along and this electron is sticking out there and they collide, it's not going to work. In other words, it must be aligned. So, the electrons can mesh. Okay? In other words, I've got to make sure that this hydrogen's flying along and this one comes, they've got to be aligned, correctly aligned, so that they will actually bond with each other. Remember all this stuff? Right. Let's continue. Whoa, that's very irritating when it does that. All right. Okay. Now, I just want to go up, page 2 of 2. Okay. Let us now do number 3 and go back to a black. Okay. Then we need number 3. These are the factors still. Number 3 is the pressure of the gas. Okay? Okay, why? Well, high pressure means what? Means that the molecules are close together. Okay? They're in a small volume. Okay? They're sitting in a small volume. So I've crunched them together, therefore I get more collisions. Don't I? If I scrunch them together, I get more collisions, which increases the chance of a product. More collisions, therefore a greater chance of product forming. I mean, this is actually logical. You just have to think about it, right? It's so logical, it's scary. The more, what do I want? I want N and 3 H's to get together and fly off to form ammonia. So the closer I can bring my N's and my H's, the more ammonia I'm going to get. If I've got one in this room of N and 3 H's, right? How are they going to find each other? I have to increase the pressure so that I put them close together. The one's going to be flying up there and the other one down there somewhere. Okay. Number 4, the last one over this, well, almost, is the surface area. Why? Okay, well, let's go back to how did we dissolve something, all right? A sugar lump, okay? If you put a sugar lump into coffee or tea, it takes longer to dissolve than if you put icing sugar in it. Why? Because the surface area. If I've got a big effervescent tablet, okay, essentially I've got that. If I put a powder, now some of you may have done this with an antacid, try putting the powder in and a tablet. The tablet effervesces, the powder goes nuts because there's lots of surface area. What does it mean? How did we dissolve a block of salt? Remember, NaCl, and over here we had Cl and Na. And what did we do? We brought water, okay, blue. So on this side I had the H, very frustrating when it does that, isn't it? This was a negative, that's a positive. So the hydrogen of my oxygen came there, and on this side my oxygen, okay, came in over here, which was the negative side, the negative side over here, right? Then I formed a bond between that, okay? And I said if the red was bigger than the lattice bond, in other words, bigger than the bonds holding it together, let me finish the black here, ClNa. So this guy is held on by this one and that one. So it's held by that and by that. If the red is bigger than those well, and that one by those three, it pulls the sodium. So it deconstructs it bit by bit. The net result is what? Is that atom by atom, it's pulled apart. Now, if I make my salt fine, it means that lots and lots of water molecules can get close. And it speeds up the reaction, right? So if I put a big block of, boom, okay, example, put a big block of coal onto a fire, or put coal powder. Don't blow coal powder through flames. It goes, it explodes, okay? Now, so that explains that. The last one, number 5, okay, is the type of substance. All right? That's pretty obvious, okay? The more complex the particle, the longer it takes because more bonds need to be broken. So let's just think, if I've got a very complex, if I've got a complex reactant, okay, what do? We need to create the activated complex. That's what we're talking about. We need to break lots of bonds, right? Hydrogen, nitrogen, just had to break those. Others, I might have to break lots and lots of different bonds to actually get the reaction to occur that we want to occur. Okay? That's going to do that. Now, I'm going to stop at that point because I've got to 30. What I'm going to do is we're going to now look at Boltzmann's graph. Okay? Wait, let me finish with number 6. Sorry. The next one is a catalyst. These are all in your book. This is a bit of book theory. Okay? I explain the catalyst like this. All right? Now, no, it's not like this, but just in our minds, it's like sticky paper. Here's my nitrogen. Boom, boom, bouncing around the room. I stick a catalyst in and it goes, gotcha. It grabs the nitrogen and it turns it so that the 3 prongs of the nitrogen are stuck up in the air. So the catalyst is like a sticky thing. So it takes my nitrogen and it holds it like that. Now it's like it's captured. So what happens next? Next is the hydrogens that are coming along, okay, have got more chance of bonding. Okay, let's put our hydrogen in over here. Because this is held still. So it's held still. Now, once those three have been put in, this is now NH3. So NH3 is released. Okay, and a new nitrogen is taken. Okay, different catalysts are going to work differently, obviously. All right, but essentially that's what it's doing. It's holding it so that you can have an effective, correctly oriented, effective and correctly aligned collision. That's what this is about. It's effective and it's aligned collision. Okay, so then we're now going to look at, next we're going to look at the Boltzmann's, Maxwell-Boltzmann curve. Thanks for watching that. We're going to get into the reaction kinetics and stuff and chemical equilibrium now. Cheers. We'll do that one next. Bye.